want to start off with some literature. I mean, like real literature. So we're going to start off with one of my favorite short stories ever, which is Jorge Luis Borges' story, The Library of Babel. Have people read this story? Yeah, it's a great story. So I'll quote you a few little bits of it, first of all, because I think what you can use the story to do is to sort of raise a really important puzzle that has been at the heart of syntax for a long, long time. So I'll just read you out this. So Borges writes, the universe, which others call the library, is composed of an indefinite, perhaps infinite number of hexagonal galleries. The arrangement of the galleries is the same, 20 bookshelves, 5 to each side, line 4 of the hexagon 6 side. Each bookshelf holds 32 books which are identical in format. And here's a lovely illustration of what the library might look like. If you look at each book, it contains 410 pages. Each page, 40 lines. Each line, approximately 80 black letters. There are 25 orthographic symbols, the space, the period, the comma, and 22 letters of the alphabet. And Borges notes that because of this, right, well, the way the library is structured is bookshelves contain all possible combinations of the 22 orthographic symbols. Okay? A number which, although unimaginably vast, is not infinite. I'll give you some sums later on where we can see just how big it is. That is all that's able to be expressed in every language. All. The detailed history of the future, I love this bit. The autobiographies of the archangels. The Gnostic Gospel of Basilides. The commentary on that gospel. The commentary on the commentary on that gospel. You can see recursion peeking in here, right? The true story of your death. The translation of every book into every language. The interpolations of every book into all books. The treatise Bede could have written, but did not, on the mythology of the Saxon people, the lost books of Tacitus. It shivers up your spine, right? So the important thing about the library, Borges' library, is, as he says, it contains an unimaginably vast number of books. So if you just think about it, basically, if we look at the number of possible books we've got there, what we want to do is take the number of symbols and multiply it by itself, the number of possible symbols that there are in a book, right? So that will give us, essentially, by the fourth multiplication, we're on 9 million, right? By the 10th multiplication, we're in the trillions. By the 100th, we're at a number greater than the atoms of the universe. But actually, Borges' library requires us to get the size of it to multiply 25 by itself over 1 million times, right? So that means if you shrink each book to the size of an atom, okay, it would still take unimaginable gazillions of our universe to hold the library. It's an awful lot of books, right? Now, most of those books are rubbish, right? Most of them are just some random collection of letters, right? So here is actually a book, or a page of a book in the library, okay? There's a great website by this guy here, Jonathan Basile, who has programmed the library. Okay, he's not really got the whole thing yet. He's only got 10 to the power of 4,677 books in it. Okay, and this is a page from one of the Library of Babel's from that particular website. And you can see it's just a random collection of letters, right? So here's the question for you. Right? Just think how big the library is. And the question is, if you're given a random sequence of letters from a book, say a sequence between 2 periods, would you be able to say whether that sequence is a sentence of the language, whatever language you speak? Okay? So it's like a sort of decision problem. We just take some random collection. So if we took this bit here and we read to here, that's the next one here, is that a sentence of English? Is that sentence of English? No, obviously not, right? So here's 2 actual cases from Basile's library, Basile's implementation of Borges' library. So there's this, which is from this volume at page number 375, okay, and then there's this, which is from this volume on page 62. You can go and have a look at them if you like, right? So this one says, and they're all there. He's generated them and they're all there, right? So this one says, an amoeba with tinnitus is rarely perplexed by water that likes to traumatize sunglasses. And this one is, I give up. Right? So it's fairly clear that one of these is not a sentence of English, right? The top one. And the other one, it's a weird thing to say, but it's a sentence of English, right? It's a perfectly reasonable sentence of English. So there's a sort of interesting decision problem, right? How do you guys decide that? I just told you how big the library is, right? It's got so many books in it, it would take unimaginable gazillions of our universe to hold the library, even if we shrunk each book to the size of an atom. It's really huge. And yet, you're able to just take any random collection of letters between two dots and say that's a sentence of English or not. And actually, it's more than that you can do, because you can actually provide a meaning for these sequences of symbols as well. Right? So I gave you a very odd sentence, which is actually from this particular implementation of the library. And it's very hard to figure out what the meaning is, but you can tell what it means, right? Odd thing to say, and you can tell what it means. And here's something that's a little bit more clear. So Anderson decided there was no way that Lily would persuade Sue that he could be trusted. Okay? So you guys know that's a sentence of English. This is going to be in the library somewhere, right? And you also know that it's possible that he there can refer to the same person as Anderson does, right? Yeah? What about this sentence here? This is another sentence from somewhere else in the library, right? He decided there was no way that Lily would persuade Sue that Anderson could be trusted. Very, very similar sentence to this one. But you guys also know that Anderson and he cannot refer to the same person here, right? So not only are you able to tell whether something is a sentence of your language, I'm saying your language rather than English, because there's lots of questions about dialect and stuff, right? The language that you speak, okay? Not only can you decide whether a sentence, or whether a sequence in the library is, a sense of your language, you also can know across an unbounded range of things what they mean and what they can't mean. Okay? So, that's quite astounding, right? At some level, we've got finite brains. So how on earth are we able to encompass this vast range of possible links between form that we see, and the meanings that they have? So it's in that sense that I think that the story of Borges' library actually, raises a puzzle which has been at the center of generative syntax for over 50 years. Okay? So given that we've got finite brains, how can we do this? Now notice that Borges' library is actually finite, right? So if we had very, very big finite brains, we could list them all, right? But there's no reason, one, we don't. We don't have brains, unless you're that robot from the restaurant at the end of the universe who has a brain the size, right? Marvin, who has the brain the size of the universe, right? Unless you're him, I guess. But we're not, so that's one question. But of course, you could also make Borges' library finite by infinite by increasing the size of the books. Right? Okay, so that's the puzzle, right? So what's the solution to this puzzle that has been given within generative grammar over the last few years, over the last 50 years. Okay? So this is a picture from my edition of Milton's Paradise Lost. I'm going to keep coming back to some literature to make those of you who feel literary feel more comfortable. So this is actually a colophon by Blake, and it's from the poem Europe. And the line that it illustrates is called "Who shall bind the infinite?" So I'm taking it as my kind of text for the day, right? So how are we able to take the infinite and pull it within the bounds of our comprehension? Okay? So Chomsky gave an answer a long time ago, which is, he's kind of updated over the years, but it's the same answer, which is essentially that language includes inside it a system of discrete infinity. Right? It's a bit like arithmetic in the way that arithmetic is a system of discrete infinity. There's an infinite number of numbers, right? But language is like that, but yet it has way more meanings than just the meanings of the numbers, right? So it's way richer than arithmetic is. Notice I said here language includes a system of discrete infinity. I've not said language is a system of discrete infinity. And that's because really all I'm interested in here is just whatever aspect of our linguistic capacity allows us to actually have this infinite range of linked conforming meaning. There's a whole lot more to language than this. So I think sometimes, people think generative linguists are only interested in formal links, but actually you know, we're interested in all sorts of aspects of language, and this is one which is a particularly interesting puzzle. So Chomsky's answer is a system of discrete infinity has these various subparts. First, there are discrete units that are relevant, so we need to think a little bit about that. It's a system, so it's governed by rules in some sense, connecting meanings with forms. And then there's no obvious limit to the number of expressions. So we need some kind of story about how to build those three things in. So what I'm going to do is essentially kind of run through these various bits of it. The discreteness part, the rule part, and then the infinity part. And then at the end, I'm going to sort of draw out some consequences of that. And at the end, I'm going to kind of give you a very brief description of an artificial language learning experiment I ran with some colleagues, which goes along the lines one might expect, as opposed to along other lines. Okay, discreteness. This might be familiar to many of you, but I'll run through it anyway. So animals, generally animals, including us, impose discreteness in certain signals we hear. So we've got fluffy clouds here. It's real hard to know where one stops and one starts. And here we've got a discrete drawing of a bunch of clouds. This is in our brain. This is in reality. Okay. So generally we interpret the experiences that come into us, which are continuous, in terms of discrete elements. So here's some evidence for that. So a very famous piece of evidence that's been known for a long, long time is categorical perception. Who here has not heard of categorical perception? Everyone knows. Well, a couple of people haven't heard of it. Okay, one person at least. So categorical perception is basically the fact that if you look at a syllable like ba and a syllable like pa, if you measure these using a spectrogram, then what you see is that there's just no clear distinction of which you can use to distinguish the b and the p. What that is, what happens is that you have essentially a longer time to begin voicing after the p case than after the b case. Okay, so you just you're closing your lips, you're beginning to go right, and then you stop voicing. Quicker versus longer, and that will give you a p versus a b versus a b. And it's the same for all of these kinds of cases. Now this is a continuous fact, right? If you measure it, it's continuous, right? But what happens actually is that people don't perceive it as a continuous thing. They perceive it as a categorical shift from b to p. So we've known since the 1970s that you can do experiments where you gradually use synthesized voices and you gradually, in tiny, tiny increments, increase the amount of time the voicing comes in after you've got the lip closure, okay, before you hit the vowel. You can increase it by very, very small fractions of microseconds, okay? And as you do this, that's a continuous increase, right? But what happens is that people perceive, 40 milliseconds actually, people perceive there to be a shift from b to p, right? And so this graph basically shows that basically people are like, yeah, that's a b, yeah, that's a b, yeah, that's a b, yeah, that's a b. Oh no, that's a p, right? And it happens at more or less the same point. There's some computations at more or less the same point, and it happens sharply. So people don't say that's bitter or pitter than that one is, right? So what you get is essentially a categorical shift, but the signal is continuous. Okay, so what we've done is we impose upon a continuous signal a discrete category. Okay? Is it only humans that can do this? Well, obviously, as well as literature, we need pictures of cute animals, right? So is it only humans that can do this? No. We've known since the 70s that chinchillas and many, many other animals are able to do this as well. They did some really horrible experiments in these poor chinchillas, like electrocuting their feet and doing all sorts of nasty stuff. It's really sad. But basically, they showed that chinchillas are able to basically do exactly the same thing as humans do. So what this tells us is that it's not just humans that impose discreteness on continuous signals. In fact, that seems to be a general fact about certain kinds of animal cognition. Okay, it's not unique to us. Okay, what about moving up a level? So we just talked about sounds, but we can also see discreteness in the way that sounds compose into units. Okay, so and we can see this from very famous experiments done in the mid-90s. On little 8-month-old babies, okay? And again, this might be something you guys know about quite well, but what Saffron and her co-workers did was they played these little 8-month-old babies, these synthesized sequences of sounds, right? So, bi, da, ku, pa, do, ti, go, la, bu, ba, etc. Right? That's how they kind of sound. And then what happens is, what they could show by certain kinds of surprisal effect that we won't go into here, what the kids are able to do is to pick up sequences of exactly the same thing that pop up out of that continuous stream. So it's a continuous stream, there's no breaks, it's just basically these various syllables, and what the kids do is they at some point go, ah, that's a unit, right? So they go, bi, da, ku is a unit, right? And the way that Safran and all propose that they do this is they attend to the likelihood of the transitions between the different syllables. So after bi, you're very likely to get da. After da, you're very likely to get a ku. After ku, you're less likely to get a pa than you were to get a da after a bi, and so on. Okay? So what the kids do is they attend to the statistical properties of the signals, and what they do is they extract out discrete units from these syllables that are pronounced one after the other. Okay? Only human? No, of course not. So other animals can do this, and here's a cotton-top tamarin, very cute little beast. And Hauser and Newport and Aslin showed that cotton-top tamarins also do the same kind of thing, with exactly the same kind of input as the infants, as the 8-month-old infants do. So they also extract out these discrete units from just a collection of syllables one after the other. Okay? Now, it's not just statistics. So human babies use all sorts of other things on top of the statistics to do this. But what they're doing is always the same thing. They're extracting out these discrete units from a signal that's not necessarily discrete. Okay? And it turns out that, for example, this is work by Jacques Meller, that newborns 2 days old are able to distinguish the same sound sequence when it's between words versus within words. So night rates and night rates sound pretty similar, right? But actually it's not the same, right? There are particular little phonotactic and phonetic properties that distinguish these things, and kids attend to this incredibly early on and are able to extract out the discrete units of bits. Okay? They also pay attention to stress patterns and various other kinds of things. So there's a lot of stuff going on in here, but it's all put to the service of the same thing, which is the same thing as we saw in the phonological categorical perception experiments. They're all with seeking a discrete units. So remember, this is just me showing you that actually, what we do with language is one part of it is this discreteness. All right, is it only humans that can do this stuff? Well, in terms of the nitrate stuff, as far as we can tell, yes. But in terms of stress, budgies can distinguish stress patterns in human words, and rats can attend to different kinds of rhythms in human words. So it looks like that all those various different kinds of things that human babies use are actually elsewhere available in the animal kingdom as well. Okay. Something about brains that, just brains somehow like to impose discreteness upon the continuous signals that they are subject to. Okay, so the third aspect of discreteness is the association of meaning with these discrete units. Okay, so you guys probably all know of Quine's Gavagai claim. So Quine was really talking here about the field linguist rather than the baby. And he said, well, look, when the field linguist is out in the field, and he has his native language consultant with him, and the field linguist points at a rabbit over there, and the consultant says, Gavagai, how do we know that means rabbit? How do we know that it doesn't mean, brown thing, right? Or thing with ears, or thing that eats carrots, or as Quine famously said, undetached collection of rabbit parts, right? So there's a sort of general inductive question. How do kids know, right, that so that's the field linguist, but you can think of it as an acquisition question as well, right? How do kids know when they hear a word, right, that word is associated with a discrete piece of meaning, right, and a stable piece of meaning? But they do, right? It's just a fact, they do. So there's a very famous fact about word learning, which is the kids seem to learn words on one presentation. It's quite miraculous, really. And they learn verbs really very happily as well. I mean, they learn nouns first, but they learn verbs quite happily, even when the event that the verb's talking about is not going on. So how do kids segment that stuff out of this stream? And how do they segment the particular meaning that goes along with it? We've got some idea, but not a huge idea. But the crucial point for what I want to say here is that they do this. Right? Okay. Is it only humans that do this? Well, I mean, if you own a dog, you probably know that dogs are able to distinguish sit and fetch, right? So even just a dog, and there's a very famous paper, a science paper, where there was a dog who managed to distinguish something like 200 human words. Okay, so animals definitely can do the same thing, where you have a discrete word unit and you associate it with a particular kind of meaning. Okay. And they can do it in the wild as well, so we'll come back to this, but here's some Campbell monkeys. And basically, the Campbell monkeys have two sounds. We'll see it's a little bit more complex than this in a sec, but basically, they go quack, and that means danger from below, probably leopard, right? Or they go hawk, and that means danger from above, probably eagle, okay? And you can test this by sort of evilly playing them hawk sounds, and they all run down from the trees, right? Animals can do this, not only dogs that we train, but they can do it in the wild as well. Okay, so this is all in, this all has 2 points, right? One point is that discreteness is crucial for human language. Human kids seem to impose discreteness upon continuous signals they're faced with, but it's not just humans that can do this. Other animals can do this as well. Those are the 2 major kind of points here. So discreteness is the first thing. Okay. Syntax, the only part of language that's not important. So we've got discrete units, and now I'm going to move on and talk about the fact that what we've got is a rule-governed system, and we'll then end up with the idea of infinity. Okay. So there's another short story. I'm going back to literature now, which is Arthur C. Clarke's The 9 Billion Names of God. It's basically the same story as Borges' Library, but kind of in a different way. So it's also a lesson about combining things. So basically in this story, it's set back in the sort of 50s or so, right, when computers weren't quite so good as they are now. An American computer firm is hired by a Tibetan lamasery to help them list all of the names of God. Okay? At which point the purpose of the universe will have been reached. Do you guys know this story? It's a good story. So the monks had kind of expected this to take them 15,000 years. They got to kind of sit down and list all these various names, right? It'd take them 15,000 years, but then they hear about these Americans and their computers, right? And they're like, brilliant, computers will be able to do this much faster. So they get the Americans to come over to build the computer in the lamasery, okay? And then and the Americans build the computer and set it going to work out the 9 billion names of God. Of course, my phone could probably do it in about 5 seconds now, but this was the 1950s. So the Americans are like, what's going to happen when the monks, when it's finished, and the monks are like, your computer must be wrong. So they're a little bit worried that there's a lot of monks, and there's only these 2 American computer scientists, so they sneak away because they're worried that the monks are going to get a bit violent once the computer finishes. So then I thought I'd read this. This is the last line of the story. Don't look down here yet. Presently, George glanced at his watch. She'll be there in an hour, he called back over his shoulder to Chuck. Then he added in an afterthought, wonder if the computer's finished its run. It's due about now. Chuck didn't reply, so George swung round in his saddle. He could just see Chuck's face, the white oval turned towards the sky. Look, whispered Chuck, and George lifted his eyes to heaven. There is always a last time for everything. Overhead, without any fuss, the stars were going out. Isn't that cool? Okay, so it's the same lesson essentially as the Borges story. The notion that you can complete essentially the number of combinations that you can have, and there's something momentous about that vast amount of combinations. And this is something which has been within human beings. Human beings have been fascinated by this for many centuries. So Gottfried Leibniz I think was probably one of the first of many people. It was Ramon Llull as well, but there were various other people to kind of really push this idea. And he had two ideas, which are very reminiscent of actually today's work, right? One of which is essentially Fodor, right? Which says that there's a universal characteristic. And what he means by that is that there is a finite set of concepts, basic concepts. Right? And then there's what you call the art of combinations, which is the way you combine those concepts. Right? And he showed that finite combination, of course, as we saw already with the 9 billion names of God, can create an awful lot of concepts. And Leibniz was interested in the notion of essentially generating new meanings from random combinations of these concepts. So I'm going to skip Bernoulli, but it's the same point. This idea was satirized by Jonathan Swift in Gulliver's Travels, and he talked about the Legado Academy, which was one of these funny places that he visited. And there was the engine of the Legado Academy, which looked a bit like this. Well, I mean, it's fictional, right? But anyway, so basically what you had is all of the possible symbols in the Legado language and a bunch of cranks, right? And you would turn, all these people would come and would turn the cranks and generate new combinations of these letters. And it was essentially a sterility on the idea that, you know, actually there is just a finite number of these, and a lot of them, as we saw from Borges' library, are just meaningless, they're just nothing. Okay, now human language doesn't work like that, right? So human language isn't every single possible combination. So I quite like this little cartoon about the fact that human languages have rules. Anyway, so human languages have rules, right? I mean, like, that's one of the things that we know about human languages. Not every combination is possible. There are only particular kind of combinations that work, as you can see by this, how specific do these errors need to be. And we know very well that basically, when we look at languages, different languages have different rules for how you put together sentences. So here's cases, this was going around Twitter a few months ago. So here's cases where we've got English at the top, I love New York. Then Welsh, love I New York. Malagasy, love New York I. Japanese, I New York love. Ishkariana, New York I love. And Nade, New York love I. Okay? So these are the putative, I'm not quite sure about this one, but anyway, these are the putative basic orders of these various languages with subject, verb, and object. Okay? So, and we know, you know, these are particular rules of these particular languages. So in English, we can't say New York loves I to mean, well, we can't say it full stop, or we can't say it to mean I love New York. Okay? So it's certainly the case that all of these orders are available, we now know, right? But in particular languages, there are only particular orders that are available. And actually, it turns out that these differ, and you probably know this, differ massively in their rarity. So some are very common, and some are very rare. And we'll come back to that in just, well, now, basically. So I should have said, if you guys want to interrupt, feel free to interrupt. I sometimes get in a bit of a kind of just stream of consciousness, so please feel free to interrupt me. So here's another case where we've got different orderings of rules. So if we take something like those three big oranges in English, that's the order those words really need to come in, right? We can't say those oranges three big or something like that, right? Okay, so I mean, you can just about get away in English. I don't know what you think of those big three oranges. Pretty awkward, but you can just about get away with it if you have certain kind of focal stress and so on. But there's definitely a basic order in English that works like this. Okay, that's a very common order for these things in languages of the world. Right? There's another very, very common order in languages of the world, which is the one that we see in Thai, which is basically the reverse of English. So in Thai, the normal unmarked order, the way you normally say, you know, if you're pointing at those, you would normally have, I'm not going to pronounce the Thai, right? You'd normally have this order. Orange, big, three, those. There's a hidden classifier in there that you can ignore. Okay, Now there's other languages, for example, a subset of the Bantu languages. Kikuyu is the one that Greenberg talks about. This is an example from Kitaraka, okay, where basically you have the order of English, but you put the noun first, right? So in Kitaraka you say, cups, these 5 red. And that's the normal basic order. At least that's the normal basic order that's reported. I say that because I did some field work on on Sibirwa, with a random Sibirwa speaker that was crashing at my place. That was like the rent, right? And actually, I was very excited to see that Sibirwa had this Kitaraka order, but it turns out actually that in Sibirwa the numeral and the adjective can commute. So actually there's some interesting work to be done to see to what extent these typological generalizations are actually true. It made me slightly skeptical. But anyway, as far as we know, there aren't any languages which are like the reverse of the English order before the noun and then the noun. So that's, Greenberg claimed that 50 odd years ago, and we haven't found a counterexample yet. So big 3, those oranges. There don't seem to be any languages that do this. So if you imagine like these words and you jumble them up, you do the combinations thing, right? There's 24 possible orders of these kinds of things, right? Of demonstratives like this or these, of numerals like 3 or 7, of adjectives like big or red, and of nouns. Only 14 of those 24 possible orders are actually tested, okay? And on top of that, as I said earlier on, these are 2 very common orders, and this is not a common order at all. So there's an interesting question that arises there, which I'll come back to when we discuss the artificial language learning experiment at the very end. And that interesting question is, why? Why do we not see 8? There's lots of possible explanations for this. One explanation might just be, well, this is common, this is less common. Maybe this is possible and just we haven't, there don't happen to be any examples of it. So it's possible that it's just rare beyond rareness, right? So that'd be one way to think about it. Another way to think about it is that, well, no, actually, in the same way as we said that particular languages have rules, right? And you can do X in a language and you can't do it in another language. Maybe language has rules, right? And you can do these things in language in general, and you can't do this thing. So those are 2 kind of competing kinds of explanations. Is it just a statistical, fact, or is there some underlying reason for it? I don't have an answer for that yet. I mean, I know what I think, right? I think that there's, language has rules, right? But I'll come back to this when we discuss the artificial language learning, which is all about this particular phenomenon. Okay, what time are we at? Have I been rambling on? Oh, half an hour, that's good. Okay. Rules, right? So remember, so we're talking about whether languages have rules, right? And remember these Campbell monkeys, so with their crack and their hawk type words. Well, it turns out that Campbell monkeys seem to have a rule, right? That correlates particular forms with particular meanings, okay? And it's a rule that appears, in the wild. It's not something that people have taught them in any sense. So this is work by Schlenker and various other people. And they've argued that actually, as well as crack and hawk, you have a ooh sound in Campbell monkeys as well, right? And the ooh sound can combine with crack or hawk in a way where it does the same job, right? So Schlenker's analysis of this is that basically crack is a general alarm, okay? And crack ooh means, oh, it's general but not very serious. Hawk is a aerial alarm, there's an eagle. And hawk ooh means, oh, it's not very serious, right? So if you hear crack, right, and you're not hearing crack ooh, and you're not hearing hawk, right, then that suggests that actually this might be quite serious. Because you've not said crack, not serious, you said crack, right? So that might be serious. So here's a sort of pragmatic explanation, but it crucially depends for why these things mean what they mean. But it crucially depends on the idea that ooh is always adding the same bit of meaning to the core meanings of these elements. Okay? So the reason that you get leopard is because crack is just a general alarm. You haven't said crack ooh, which means not serious. That means crack is serious. And it's not hawk, so it's not aerial, therefore it's a leopard. Right? So that's the basic story that Schlenker gives for this, and it's a reasonably convincing story, I think. But it's a rule, right? It's a really interesting rule that says we've got meaning, we've got form, and we're adding to that meaning in a very consistent way. Okay? But it's only finite, and this is a really crucial thing about rules of this sort, to the extent that we find them. It's pretty hard to find them, to be honest, in non-human communication systems. Okay? It's a very small number of these. I mean, basically, it's basically ooh. Your rule is add ooh to the two words that you've got. That's not a big grammar, right? I mean, if we are thinking about going back to Borges and his library, you're not, I mean, sure, you're going to find clack, clack, ooh, hawk, and hawk, ooh in Borges' book, but it's not very impressive really, compared to what human beings can do. Okay, so there are rules. Non-human animals seem to be able to a very limited extent, use rules that associate form and meaning. Okay? But humans seem to have a much wider capacity than this, which we'll now turn to. Which is that, so what we've done so far then, going back to Yoda, we've seen that we've got discrete units. We've seen that human language is a system, so governed by rules linking form and meaning. We've seen that non-human animals have discrete units. We've seen that non-human animals have a version of this. Right? Pretty limited, but definitely a version of this. So the last thing, and the reason why Chomsky's always going on about this, is the thing that seems to distinguish us from other non-human animals. Right? Okay. So this takes us back to the lesson for today, who shall bind the infinite. And I quite like this little cartoon here. We've got mathematicians writing here, and in the middle, then a miracle occurs. Right? So what is this miracle that allows us to essentially take whatever animals have and then turn it into something which gives us the vast range of capacities that human beings seem to have? Okay, so the story here is that, well, the first question is, so how do we define gigantic sets? In fact, potentially infinite sets. Okay? And actually, historically, no one really knew how to do this for a long, long time. It was only really in the 19th century that people began to have a formally clear way of really understanding what constitutes an infinite set. The question of infinite sets has been a question since the start of mathematics, right? So Aristotle believed there was no infinity, there was only the potential to continue adding. Leibniz, we saw earlier on, had this like vast combinatorial system that didn't know how to make it do an infinite set of things. But actually in the 19th century, a bunch of mathematicians and logicians came up with ways of really properly understanding what it means to be an infinite set and how you can tell whether something is in an infinite set or not. Okay? So the first of these, I mean, not the first, it's hard to disentangle the intellectual precedents here, but at least Giuseppe Peano, in his attempts to build the foundations of arithmetic, proposed a way of defining the infinite set of numbers in a finite way. Right? So, I mean, what used to happen is you would say, okay, well, we define the infinite set of numbers by going, 1 is a number, 1 plus 1 is a number, 1 plus 1 plus 1 is a number, dot, dot, dot. And you're meant to use your intelligence to realize that dot, dot, dot means 1 plus 1 plus 1 plus 1 is a number, right? But dot, dot, dot doesn't say that. Dot, dot, dot just says, you do it, right? Sorry?
Keep going.
Yeah, keep going, right? But like, what does that mean, keep going? So Peano had a way of essentially defining what it means to keep going in a finite way, right? So he said 1 is a number, and then if n is a number, then the successor of n is a number. Right? So you can define what a number is as long as you know what successor here means. Okay? You can define what a number is on the basis of saying there's a certain set of things that are numbers, in this case just 1, right? And then you've got this recursive clause that says if something's a number, then some function of that thing is a number. Okay? And then we have to ask what the function is. Okay? But that is a way of getting rid of the dot, dot, dot. Right? Because what that does is it tells you explicitly what the set of things really is. Okay? So actually, before I go on, I just want to point out that this finite definition of an infinite set is kind of closely tied to the Borges puzzle we started off with, right? Because the Borges puzzle was, well, just see this gigantic set, which we could make infinite if we wanted to, but it's just absolutely gigantic. How do we decide what things are in it and what things are not in it? How do we decide whether senses of our language, how do we extract out of the Borges library the senses of just our language? Right? How do we know, given any sentence that's in our language or not? We do, but how do we know that? Okay. All right. So I gave you here this notion of successor, right? So we've got some function on n being a number. So what is that? Well, there are a couple of ways to do it, but one famous way was suggested by John von Neumann, and he said, okay, well, let's use sets here. Okay. I'm sorry for the maths here. I gave you literature at the start, we're doing maths now. Keeping the balance between literary and it's C.P. Snow's two cultures being brought together. Von Neumann suggested using sets to do this, right? So he said, well, let's define 0 as the empty set. Okay? And then we will define the recursive clause of this to say that the function, the relevant function on n is n union the set containing n. Okay? So 0 we know is the empty set. 1 will be the empty set union the set containing the empty set, right? Which is the set containing the empty set. Okay? 2 is that thing we just built up, which was 1. That's our n now. Union the set containing that thing, right? Which gives us this structure out in the end. And so what you end up with is a larger and larger collection of structures. So numbers, under von Neumann's definition, are just structures, right? Okay. So we actually have a way of understanding what the successor function is, right? It's essentially a way of building structure. And that is the thing that allows you to define what an infinite set is, right? You start off with a base case, and you define your successor function, right? And the successor function builds larger and larger structures in a very kind of like nailed down fashion. Okay? Now, I was about to say that's not very interesting. It is incredibly interesting. Some level we can build the whole maths out of this basically, right? So it is extremely interesting, but the really interesting thing is you can use this technique really to begin to get to the solution of the problem of what's in Borges' library. Why am I telling you about Turing machines next? Why am I telling you about Turing machines? Okay, I'll ignore Turing machines just now. I'm going to come back to them in a second. Okay, so Chomsky way back in the 50s made two proposals about syntax which basically riff off of what I just told you, this notion of the successor function for defining the infinite set of numbers being the core of what gives you the ability to define an infinite set of elements. Okay? And defining an infinite set of elements is the thing that allows you then to define the relationship between form and meaning across an infinite domain. Okay? So Chomsky made these two proposals. The first proposal is that human language is actually computable. That's why I was giving you Turing. Okay? So, we talked about the recursive definition, we talked about this successor function here, right? From von Neumann to build numbers. Now, there's a whole bunch of logic and maths going on at the time, which was an attempt to sort of say, well, what are the basic functions that you need to define infinite sets? And the successor function is one of them. There are a bunch of other ones, which we can talk about if you like, but it's not a maths class, so I won't. But probably the best story for this was Turing's story, right? And what Turing suggested was that you can build a little kind of machine which will, allow you to compute whether something is in an infinite set or not. And it was shown that Turing's little machines were identical to the set of basic functions from which you can use to build the numbers up from. Okay? So there's two different intellectual strands going on here. One intellectual strand was an attempt to build an understanding of infinite sets using these little functions, like the successor function. Okay? And another strand invented by Turing was essentially computers. Okay? And then there was a bunch of proofs that showed that they were identical, these things. So recursive functions, basic recursive functions you can build up infinite sets of numbers with, and the notion of a Turing computer are the same thing. Right? Provably the same thing. So this, I think sometimes in the literature there's a bit of a mess up about this, and people talk about recursion in language, right? And there's sort of questions about it being recursive structures, and you guys probably all know these debates, right? But actually, really, the core notion of recursion that's relevant for what we're talking about here is exactly the same as the notion of computable. Now, not everything is computable, so that was one of the big things that Turing showed. Not everything's computable. There are infinite sets that are not computable, right? The real numbers, for example. There are various sets that are not computable, but there are some that are. And now we get back to where I wanted to be, which is that Chomsky's proposal is that human language actually is computable. That is, there is some function, a computable function, which lies at the heart of what makes human language. Which lies at the heart of our ability to pick out from Borges' library the sentences in English, or in Kiowa, or in Lungabuyu, or whatever, right? So, so that's one core thing, and not everyone believes this. Right? So many people think that language isn't computable. In fact, I think if you work in cognitive grammar, you just don't think that this is how things work. Right? You don't believe that human languages are computable in the same sense. Okay? The second aspect is very closely tied to this, which is that the way the human language works is very much like the way that the numbers work that I just gave you, which is that there is a recursive definition of structures. And those structures involve hierarchical embedding, and because there's no limit to it, it's an infinite set,